Good evening, all. Welcome to Unacademy. Good evening, everyone. My name is Bhanu Prakash, expert in GATE and ESE coaching. I did MTech from NIT Kurukshetra. I have 10 plus years of teaching experience. I expertise in the subjects of electrical machines and power electronics. BPC 10 is my referral code. Use this code, you will get 10% to discount on plus subscription as well as iconic subscription. And what are the benefits of the plus and iconic subscription? By taking plus subscription, you can get the live classes from the top educators of the country, and also you can get structural schedule, unlimited practice questions per subject wise and topic wise, and also weekly test series. So by using this, you can analyze your performance, and it is very useful for your GATE and ESE preparation. And another subscription, that is iconic subscription. By taking iconic subscription, you can get all these four benefits, and in addition to these, you will get personal coach, study planners, and expert guidance, and ESE mains questions and answers. Personal coach means that is a one-to-one guidance for your GATE and ESE preparation, and also we will provide the study planners, expert guidance, the ESE mains questions and answers. Okay, this is a very useful for your ESE preparation. So use my code BPC10. Okay, for this is my referral code. So use this code, you will get 10% to discount on plus subscription as well as iconic subscription. And what about the price for the plus and iconic subscription? Plus subscription is available for 12 months, 18 months and 24 months. Okay, for 12 months fee is at 27,225 rupees. For 18 months fee is at 34,650 rupees. For 24 months fee is the 39,600 rupees. And another subscription, that is iconic subscription. So by this iconic subscription is available for 12 months and 24 months. For 12 months fee is 45,225 rupees, and 24 months fee is 66,600 rupees. Okay, how to install Unacademy learning app? So go to Play Store and search Unacademy learning app and install this app in your phone and our laptop. Access all pre-special classes. So to invite this pre-special classes, so use my code BPC10. Okay, it is my invitation code for the special classes, and also referral code to get the 10% discount on the plus subscription as well as iconic subscription. So this is a Unacademy GATE Telugu December month schedule. Communication system 4 to 5:30 p.m. Electrical machine 4 to 5:30 p.m. Engineering mathematics 5:45 p.m. to 6:45 p.m. Power system 7 p.m. to 8 p.m. Aptitude is 8:30 p.m. to 9:30 p.m. So this is the regular batches. Okay, here communication system is dealing Nageshwar sir, and engineering mathematics is subject is dealing Venkat sir, and power system is dealing Surendra Bab sir. Aptitude is Ellen Sharma sir. Okay, remaining cross batches, that is power electronics from 4 to 6 p.m. EDC is 4 to 6 p.m. and aptitude is also 7 to 9 p.m. So these are the plus batches taken by the top educators of the country. So per EEE and EC, one of the batch for the target years prelims 2021 electrical batch, and another batch rank booster batch for GATE 2021. So another batch for the EEE target ESE prelims 2021 batch C, and rank booster batch for the GATE 2021 electrical batch B. So these are the plus batches taken by the top educators, and this is the notification for legendary educator. So the date will be revealed soon and in our channel, Unacademy GATE Telugu channel. And some batches, exciting batches for the GATE 2021, Evalve GATE 2021 ECE Batch A, which is in English and also in the starts on December 21st December, today itself. So take the subscription as early as possible today only. So use my code BPC10, it's my referral code, and these are the top educators taken by these batches, that is a Vishal Soni sir, Suresh sir, Siddha sir, BV Reddy sir, and eval batch for the GATE 2021 electrical batch A, which is in English and Hindi, starts on 21st December. So some of the top educators of the country are taking these batches. Okay, Ankit Goyal sir, Ajay Gupta sir, Kwasif Apis sir, BV Reddy sir, Suresh VSR sir. Okay, listen. In previous class, we had discussed about armature reaction of the DC machine. Similarly, commutation of the DC machine. What is the mean by commutation? What are the types of the commutation in the DC machine? And basically, what type of commutation occur in the DC machine? Delayed commutation occur in the DC machine due to reactance voltage. Okay, and also cross magnetizing effect of armature reaction. This part we had discussed in the previous class. Okay, in this session I would like to discuss about the types of the DC generators. So DC generators are classified based on the excitation of the field winding. So what is the meaning of excitation? The excitation is nothing but the process of giving energy to the field winding, or the process of giving energy to the field winding to create magnetic field or to create the flux is known as a excitation. So based on the excitation, these generators are classified into two types. One is the separate excited DC generators and self-excited DC generators. Okay. So first let us know about what is the meaning of excitation. Excitation means the process of giving energy to the field winding. Energy to field winding in order to create magnetic field, or in order to create flux in the machine. Okay, which flux here? So this flux is known as a main field flux of the machine. So this is a the field flux of machine. So which is denoted by phi f here. So this flux only induce the EMF in the generator. Suppose in case of the generator, so this you can write. Okay, so generated voltage directly proportional to the speed of the generator and the main field flux phi f here. It is a product of the speed and main field flux. So this is in case of generator part, and in case of the motor, okay, it is the torque produced in case of the motor it is directly proportional to product of the main field flux and armature current. So in the previous class also I have mentioned that the armature current is a desirable to increase the current, increase the torque in the machine, but armature flux is undesirable. The here is a main field flux is a phi f. So where is a phi f in the sense main field flux. So that how do we define excitation? The process of giving energy to the machine or energy to the field winding in order to create the flux or useful flux in the machine is known as the excitation here. So based on the excitation, DC generators are classified into two types. So one is a separate excited DC generator and also self-excited DC generators. What is the meaning of separate excited DC generators? So that you can write. So DC generators based on the excitation. Based on excitation. Okay, so these DC generators are classified into basically two types. So one is a separately excited DC generators. Separate excited DC generators. Okay, and second one is a self-excited okay DC generators. Got it? So what is the meaning of separate excited DC generator and how do we develop this separate excited self-excited DC generators here? In separate excited DC generator, there is a separate voltage source to excite the field winding. But in self-excited generator, there is no such type of arrangement. Armature current itself the excite the field winding of the DC generators. So that's why it is treated as a self-excited DC generators. Okay. And again, these self-excited DC generators are the basically classified into three types. So one is the DC, the shunt generator, and second one is the DC series generator, and third one is the DC compound generators. Basic classification of the DC generators here. Again, compound generators are classified the long shunt compound generator, short shunt compound generator based on the connections. Okay, and this is the self-excited generators are classified. So based on the connection of, okay, this is the connection of armature winding terminal and field winding the terminals. Okay, based on the connection of armature winding terminal and field winding terminal. So these are classified into three types. One is the DC shunt generator, DC series generator, and DC compound generator. So DC shunt generator means the field winding terminals are connected across the armature winding terminals. In DC series generator, the field winding terminals are connected in series with the armature winding terminal. So in case of the compound generator, some part of the field winding is connected in series with the armature winding and some part of the field winding turns are connected across armature winding terminals here. That's why it is treated as a compound generators. Got it, point? So basically based on the excitation, okay, this is the based on excitation. So these are classified as self-excited DC generator. and separate excited DC generators. Again, cell is classified into DC shunt generator, DC series generators and DC compound generators. Okay, is that clear? Okay, listen. In separate excited DC generator, so there is a separate voltage source that to excite the field winding. So that current is a field current IF and field resistance is a RSH R the F value. Okay, shunt field resistance, field resistance. RA is the armature resistance, EB is the back EMF, and this is the back or generated voltage, the EZ. Okay, generated voltage EZ values here. So in separate excited DC generator, there is a separate voltage source to excite the field winding as shown in the figure. In separate excited DC generator, there is a separate voltage source to excite field winding as shown in the figure. Got it? So here whenever we know magnetic field, so when the field winding is excited with the DC supply, the steady nature of the magnetic field will be produced. Okay, this is the steady nature of magnetic field. So this flux we can treat it as a magnetic flux phi F1. So now when this armature is rotated by the prime mover, okay, it is rotated by prime mover. So then what will happen here? So whenever this is a magnetic field, whenever a rotating conductor is placed in the stationary magnetic field, an EMF induces in the armature. That EMF is called EZ here. Or this the under loaded condition, armature current starts flow in the load terminal as shown in the figure. So when the field winding is there, so in separate excited DC generator, there is a separate voltage source to excite the field winding as shown in the figure. So next point, see, so whenever, okay, this field winding, when field winding is excited with the DC supply, excited with DC supply, steady nature of the magnetic field. Magnetic field will be produced. Okay, so according to the Faraday's laws of electromagnetic induction, EMF induced in the generators. According to Faraday's laws of electromagnetic induction, so EMF induced in the generator induces in generator and thereby armature current flows through the load. Okay, so this is the theoretical part about the separate excited generators. And what is the terminology used in this separate exit DC generator? So let us assume here EZ is the generated voltage. So let the EZ is generated voltage of the generator. Okay. And VT is a terminal voltage. And IA is armature current. Okay, RA is a armature resistance. Armature resistance value. So from here we have to find out what is the voltage equation, current equation and the power equation, where IF is the field current. Okay, field current one. So let us find out first one, the voltage equation or current equation. Voltage, sorry, let us find out current equation initially. Okay, so from this diagram, how do we get current equation? IA is equal to IL, where IL is equal to output power divided by the terminal voltage. Armature current IA is equal to IL, so that equal to output power divided by terminal voltage. So which was given in the nameplate details of the machine. And next one, after getting IA, so let us find out voltage equation. Voltage equation. So apply the KVL in this loop. Okay, by KVL equation. By KVL. So voltage rises are equal to voltage drops. So by KVL equation, so voltage is equal to terminal voltage V, generated voltage, the EZ is equal to the terminal voltage VT, okay, plus armature resistance drop IARA, the plus some brush drop. Okay, so this brush drop is a very small, okay, very small value. Okay, it is almost the 1 volts per brush. Okay, it is a very small, so neglected analysis point of view. Okay, if it is a neglected, so then generated voltage is equal to, okay, easy. So that is a VT plus IARA. So sometimes this equation is treated as a generator KVL equation. So this is the generator, the KVL equations. Okay, and next one, let us find out power developed in the armature. So this is the current equation, okay, and voltage equation and power developed in the armature. Third one is power developed in the armature. or power equations. So how do we get power developed in the armature here? So that armature power developed in the armature, so that equal to generated voltage EZ multiplied by armature current. Okay. So this is the for any type of generators. Current equation, voltage equation and power equations. Okay, are power developed in the armature. All of you got it? So per example point, we have a, let us take one example. So that is a nameplate details of DC generator. DC generators are given as follows. This is the nameplate details. So for example, 200 volts, okay, 10 kilowatts, and here the 10 kilowatts, 200 volts, armature resistance is equal to 1 ohm. Okay, some nameplate details of the generator. So this 200 volt voltage rating mentioned on the nameplate details of the generator, it is always the terminal voltage only, but not the, this is a, but not the generated voltage. Okay, voltage rating mentioned on the nameplate details, so that is the terminal voltage only. And similarly, power rating mentioned on the nameplate details, so that is a output power of the generators. Output power of the generators, or the output power of the generators. Got it, fine? The nameplate details of the DC generators are given as follows. For example, 200 volts, 10 kilowatts. That is a here armature resistance is equal to 1 ohm. So where RA is the armature resistance. Resistance 1. So now let us find out. So what is the generated voltage and power developed in the armature? So first one, armature current IA is equal to, how do we get armature current IA? So this IA value is equal to, so here in case of IA, so that equal to IL, okay, it is equal to output power divided by terminal voltage of the generator, so that is a VT. So output power is equal to 200 volts, output power is a 10 kilowatts, 10 into 10 to the power of 3 divided by 200 volts. Okay. Now it is equal to how much? The 10 to the power of 3 divided by 200. So it is a 50 amps. Okay, this is the armature current. So now let us find out the generated voltage. So where EZ is equal to the VT plus IA RA. This is the generated voltage equation. So from here the VG is equal to, so generated voltage VT is the 200, okay, plus IA is a 50 multiplied by armature resistance is a 1. So now this value is equal to 250 volts. And next one, so let us find out power developed in the armature. So that value is equal to EZ multiplied by armature current. So where EZ is equal to the 250 multiplied by the 50 amps. So now let us find out what is the value here. So this value is equal to, okay, 12.5 12.5 kilowatts. Okay, so this power is a net to mechanical net power, okay, net output power. So if here is there is some mechanical losses, that's why power developed in the armature is a 12.5 kilowatts. If remove the electrical losses, then we will get the 12 point, the actually here 12 power developed in the armature is a 12 point kilowatts, but actual output at the load terminal is a 10 kilowatts. Okay, some problems given that suppose DC generators, and there are the another types also there, series generators, shunt generators, okay, compound generator, long shunt generators. So in the any question, unless otherwise specially mentioned, DC generator in the sense separate excited DC generators only, okay, in the problems point of view. So if DC generator is mentioned, so which generator we have to take, we have to be consider whether it is a separate exit generator or self exit generator, series generator, shunt generator and compound generators. So to avoid the confusion, the generator is mentioned unless otherwise specially mentioned, the DC generator in the sense separately excited DC generator only. Okay, so very important note for the problems point of view. This unless otherwise specially mentioned, DC generator in the sense separately excited DC generator only. Okay, so this is about the discussion separate excited DC generators. Okay, got it all of you? Okay, next another type of the generator, that is the self-excited DC generators. Okay, so we already known that in separate excited DC generator there is a separate voltage source to excite the field winding. Okay, but in self-excited DC generator there is no such type of arrangement to excite the field winding. Armature current itself will excite the field winding of the DC machine or DC generators here. But there is some contradiction in the statement. See here, in order to produce or in order to generate the voltage in the generator, the magnetic field is required. To create that magnetic field, armature current is required. Then how does the EMF will be built up in the self-excited DC generators? So I repeat the once again, listen, very very important. In separate excited DC generator, there is a separate voltage source to excite field winding. But in self-excited DC generator, DC generator, there is no such type of arrangement Am I right? There is no such type of arrangement to excite field winding. Armature current itself excite the field winding. Excite to field winding of the DC generator. Field winding. Got it? The field winding of self-excited DC generator. So, but our question is, in order to create, okay, how do we create this? How do we produce this? How do we get this armature current? So, in order to get armature current, magnetic field is required. But to get magnetic field, armature current is required. So, there is some contradiction in the self-excited DC generators. Got it, my point? In order to get armature current, magnetic field is required. Okay, in order to get armature current, magnetic field is required. Similarly, to get armature current or to get magnetic field, armature current is required. Similar way, to produce magnetic field in the machine, okay, armature current is required. Got it? So then how does, okay, then how does EMF build up or generated in self-excited generators? Okay, there is some contradiction, but there is no this type of things in the separate excited DC generator. Why? Because see here, so whenever field winding is excited with the DC, there is a separate voltage source to excite the field winding. So when field winding is excited with the DC supply, steady nature of the magnetic field is produced. A rotating conductor is placed in the stationary magnetic field and EMF induced in that conductors. So under loaded condition, armature current passes through the load terminals. But here there is no, okay, in this case, listen, what will happen? So in separate excited generator, there is a separate voltage source to excite the field winding. But in self-excited generator, there is no such type of the arrangement to excite the field winding of the machine. Armature current itself, okay, this armature current itself the excite the field winding. But what will happen? In order to get armature current in the machine, magnetic field is required. Similarly, to produce the magnetic field in the machine, armature current is required. Then how does EMF build up in the self-excited DC generators? Okay. So in order to build up of voltage in the self-excited DC generator, some conditions must be satisfied. Otherwise, it fails to build up of voltage. In order to build up of voltage in self-excited DC generator, DC generator in order to build up of voltage in the self-exit DC generator, some conditions must be satisfied. Such as, so what are the conditions to be satisfied to build up the voltage in the self-exit DC generators? So first one is this first one, the field poles have some residual flux. Okay, condition 1. So this is the condition 1. So it is a field poles have some amount of the residual flux. Field poles should have residual flux. Okay, so now we have a question. What is the meaning of the residual flux? Suppose if there is no residual flux. Okay, first condition 1 is the field poles have some residual flux. So what is the mean by residual flux? It is a small amount of the flux present in the any magnetic material without any magnetizing current. Okay, at the suppose this is the small amount. What is the residual flux means? It is a small amount of residual flux. So it is denoted by phi r. So very small amount of the flux present in the magnetic material without any excitation. Okay, that is a small amount of flux present in magnetic material without any excitation. Okay, so that means suppose if we draw the curve between the flux and the field current, okay, IF, this is the exciting current in the DC machine, field current. So now it is the field flux IF. So without any flux, okay, without any current, so there is some amount of the flux present in the material. So this flux is known as the residual flux. Okay, phi r here. Suppose if there is no residual flux in the machine, a clear point. Condition 1 is the field poles should have residual flux. So what is the meaning of the residual flux? Small amount of flux present in the magnetic material without any excitation. So now we have a question. There is no residual flux in the field poles. Then how does EMF build up in the self-exit? How do we get residual flux in the field poles? Okay, this is the one of the question. So there is no residual flux in the machine. Then how do we re-establish residual flux in the field poles here? So if there is no residual flux in the field poles, it can be re-established by using the field flashing method. Okay. So if there is no residual flux in field poles, then it can be re-established by using field flashing method. Okay, So what is the mean by field flushing method? This is also one of the question. So if there is no residual flux in the field poles, how do we get the residual flux here? How do we re-establish residual flux in the field poles? So here, establish in field poles, okay, in the poles, subfield poles, by using the field flushing method. So what is the meaning of field flushing method? So for example, so this is we have taken the field winding of the machine. It is the field winding. So okay, and it has a terminals of F and F dash. Okay, field winding terminals. So it is excited with the separate voltage source, the up to about 30 minutes. Suppose we have excited with a separate DC source. Okay, here the DC source, the separate sources, and here we switch is provided. Okay, there is a switch here. Okay, switch, yes. Okay, so now initially the field current is as a field current is equal to 0. Okay, this one is a IF, the field current, and flux in the field winding, okay, phi F. So as a field current here 0, okay, at the initial stage. So initially here, so IF is equal to 0 and phi F also equal to 0, right? So this is the initial condition. So then finally what will happen, see, so as a the fluxing here, when the switch is closed, then what will happen? So when the switch is closed, current passes to the field winding. So there is a number of the turns, okay, n turns of the field winding, turns, TF turn. So therefore flux here. So when switch is closed, okay, when S is closed, then what will happen? The current here, okay, current, the field current starts close to the field winding IF. So here MMF setup initially. So what is the MMF, field MMF here? Number of turns multiplied by the current passes to the field winding IF, number of the turn. So due to which, okay, this is the field flux phi F. So that phi F is equal to MMF TF multiplied by ampere turns divided by the reluctancy of the reluctancy of the core. Okay, this is the reluctancy of the core here. So as a field current increases, okay, see here, as a field current increases, so field flux also increased linearly. So increase the linearly up to what point? Up to the saturation point. So beyond that, as a field current increases, there is no, okay, here. So this is the saturation as a field current increases here. So it is the increment, okay, and the increases up to the saturation point. So beyond the saturation point, even though field current increases, there is no increment in the flux. So now switches are open. After this, okay, here as IF increases, okay, IF increases, so then phi F also increases and reach to the saturation level. So now switches are open. Then switch is open. Then what will happen? So it cannot follow the same path. So it traces the another path because of this saturation. So now this is another path. So this method, okay, is known as so it is this small amount of flux is known as the residual flux. So this process is known as a field flushing method. So in field flushing method, the field winding is excited by using the separate voltage source, the nearly about 30 to 40 minutes or 20 to 30 minutes. So after that, when the switch is closed, so current becomes 0. Okay, here the initially here. So at the time in the process here, okay, process IF, as a IF increases, the phi F also increasing. So finally what will happen? When switch is open, So then IF here comes to 0, but this phi f comes to the small value. So that flux is known as a residual flux. Okay, all of you clear? What is the meaning of the residual flux? It is a small amount of the flux. Okay, it is small amount of the flux, the present which present in the magnetic material without any excitation. Okay, am I right? Is that clear? So next one, the condition 2. So one more condition to be satisfied. So what is the condition 2? The field winding terminals are properly connected to the armature winding terminal. So in such a way that initial field flux is aiding the existing field flux, existing residual flux. Otherwise, machine cannot build up of the terminal, build up of voltage in the self-excited DC generators. So, for example, point here we have taken example. So, example point, the shunt generator. Okay, shunt generators here. So, what is the shunt generator diagram? Armature winding terminal. It is the armature. Okay, generated voltage here easy. Let us assume positive and the negative. So under no load condition, your load is connected here, there is no problem. So now field winding is connected. Okay, this is the field winding of the shunt generators. So field winding is connected across these terminals. Armature terminal is A and A dash, and field winding terminals is a, okay, this one is a field winding F and the F dash terminal. So there is a small amount of the flux here, residual flux. Okay, now it is rotated by the frame mover. Okay, this one is rotated by frame mover in the clockwise direction at a speed of the n. Okay, this is the shunt generators. So what will happen? See the condition 2 here. The field winding terminals are properly connected to the armature winding terminal. So that is this is a positive. Okay, and with respect to the A dash, the F is a positive with respect to the F dash here. So field A, the positive terminal is connected to the positive and negative terminal is connected to the negative. So field winding terminals are properly connected to the armature winding terminal in such a way that initial field flux is aiding with existing residual flux. Otherwise, what will happen? The generator fails to build up of the voltage. Okay. Condition 2 is a field winding terminals are properly connected to armature winding terminals in such a way that initial field flux must aid to aid with must be aiding with, just wait a minute, in such a way that, okay, initial field flux is is aiding with existing residual flux. Okay, otherwise that means here polarity of the armature winding terminals, polarity of the armature winding must be same as that of field winding terminal. Polarity of field winding terminal must be same as armature winding terminal polarities. Okay, so otherwise your generator fails to build up of the voltage. So now let us take the one by one point. So case 1, so we have taken as a case 1. So polarities are same. Polarities of two windings are same. Then what will happen? See, so initially there is some amount of the residual flux. Okay, so initial flux is equal to so residual flux is present. The field poles have residual flux pi r. So after that what will happen? So initially there is just field poles have the residual flux. So after this, okay, this the residual fluxes. So whenever a rotating conductor placed in the residual flux, so EMF induces, okay, that EMF you can treat it as a EZ1. Okay, so when EZ1 is induced, which in turn produce the current IF1. Okay, current passes the field winding. Some amount, suppose if the load is connected, so some amount of the current passes through the load terminal, some amount of the current passes to the this IF, okay, field winding terminal. So when this IF1, the create the flux of the phi F1, okay, phi F1. So here this is a phi F1, okay, phi F1. So now after this what will happen? There is a phi F1 and when these polarities are equal, the polarities are same. What is the net flux in the machine? So net flux here, okay, net flux phi net is equal to, so phi r, okay, plus phi F1, okay, phi F1. So next one, this will be induced as the EMF of the EZ2, okay, EZ2 here. So now this EMF the produces the current of the IF2, okay, this IF2 values here, and again this flux produces the here, so phi F2, okay, phi F, so this is the current phi F3 here. So now after the phi F3, what is the net flux in the machine? The net flux is the, so phi r plus phi F1, this is a phi F2, right? So this is the plus the phi F2 values here. So this process will be continuous. Okay, this process, the continuous up to field poles get saturated. So up to the saturation point. So like this voltage will be built up if the polarities are same. Suppose in the case 2, okay, let us take, so polarities are opposite. Okay, this is the case 2. Okay, opposite polarities. Then what will happen? See, opposite polarities. Okay, suppose initially there is some value of the residual flux phi r. So because of the rotating conductor, the EMF induces, okay, that is the EZ1. So this EZ1 that produces the current of the IF1. So again this IF1 passes to the number of the turns, the flux will be produced. So this flux is called the initial field flux. Okay, initial. So due to this opposite polarity, then what will happen? The net flux is equal to, so residual flux minus the phi F1. So whenever this is there, when the phi F1 is equal to phi r, so what is the net flux in the machine? The phi net is equal to 0. When phi net is equal to 0, generated voltage in the machine will become 0 here. So that's why in order to build up of the voltage, the field winding terminals, polarities of the field winding terminal, the must be same as that of the polarities of the armature winding terminal. Otherwise, what will happen? Generator fails to build up of the voltage. Okay. This is the condition 2. So next one, condition 3. Another condition 3 here. So what is the condition 3? That the speed of the generator, okay, speed of the generator must be above its critical speed. Okay, this is the condition 3 is a speed of the generator must be above its critical speed. Okay, so now we have a question, critical speed. What is the meaning of critical speed? It is denoted by NC. So let us assume the speed ranges, okay, like these are the speed ranges here. So in this case, initially 1 RPM, okay, per example 1 hour, and it is a some 50 RPM, and this is the 1000 RPM here, okay, and it is the rated speed. So initially it starts from the 1 RPM to 50 RPM, okay, 50 RPM. So initially here there is a satisfy the two condition. So but generated voltage in the generator, okay, EZ is equal to here. So in this range, generated voltage in the generator is equal to 0. So here in this range, generated voltage in the generator not equal to 0 here. So now it start the generating voltage at 50 RPM. So now this is called as a critical speed NC value. So that is the speed of the generator, okay, speed of the generator, the below which generator fails to build up of the voltage is known as a critical speed. Okay, so that's why another condition required to build up of the voltage, the speed must be above its critical speed. Okay, otherwise generator fails to build up of the voltage. So now this is the critical speed means critical speed NC. Okay, it is the speed of the generator below which generator fails to build up of the voltage. Okay, so it is the speed of the generator, the below which generator fails to build up of voltage is known as critical speed. Okay, and next condition 4. Okay, so another condition is required to build up of the voltage, that is the resistance of the field winding must be less than the critical resistance. Resistance of field winding must be less than the critical resistance. Okay, so now we have a question. What is the meaning of the critical resistance? Okay, how do we define critical resistance here? So let us assume this is the resistance here. Okay, so 1 ohm and the range, the resistance of the field winding, it is a the 400 ohms, for example 4. So now here this is the 300 ohms. So in this range, when the resistance of the field winding is less, okay, that is the generator voltage can it can build up of the voltage. So now it is a more than the 300 volts, that is a higher value. So field current will be, as a resistance is high, so then what will happen, as a field resistance is high, okay, current here, the current if is a will be low. When if is a low, so that is the flux is a very low one. So when it is a flux is a low means the reduces to the very zero values here when it is a high. So that's why this the generated voltage in this range is equal to 0. So this resistance is known as a critical resistance here. So that resistance of the field winding. So it is a resistance, critical resistance means critical resistance. It is denoted by RC. So it is the resistance of field winding below which, okay, below which, sorry, resistance of the field winding above which generator fails to build up of the voltage. Build up of voltage. So this is a critical resistance. So in order to satisfy, in order to build up of the voltage in the self-excited DC generator, these 4 conditions are satisfied. So if any one of the condition is not satisfied by the generator, it cannot build up of the voltage. All of you clear my point? So any condition, if the generator is, if generator, note, if generator satisfy all 4 conditions, then satisfies all 4 conditions, then it can build up of voltage. Okay, otherwise, so what will happen? So otherwise it cannot build up of it fails to build up of the voltage. Generated voltage will become 0. Okay. And one more condition, in case of the series generator, in case of series generator, okay, so here load must be connected, must be connected in the excitation process. Okay, otherwise what will happen? Generated voltage will become 0. Why? Because there is no closed path in the series generator. Series generator means, so here armature winding, the field winding is connected in series the field wind. So if there is no, it cannot build up of the voltage. Okay, EZ is equal to 0. So that means the otherwise generator fails to build up of the voltage, almost 0. So because of the residual flux, there is a some value, it is a very small, so neglected. So if it is a load must be connected to excite the field winding. So that's why what we have to do here, in order to here, the DC series generator cannot build up of the voltage under no load condition. It is a very small due to the residual flux which is neglected. So in order to build up the voltage, the load must be connected. Okay. So these are the discussion about how does voltage build up in the self-excited DC generator. So now let us discuss one of the generator, that is the shunt generator. Okay, in the shunt generator, okay, it is the EZ and the VT values. So in case of the shunt generator, field winding is connected the across the armature winding as shown in the figure. Okay, and this the RSH is the field resistance, RA is the armature resistance, IL is the load current, IS the shunt field current, armature current, and load terminal voltage. So now let us find out one by one. So this is a first one, terminal voltage or current equations. Current equation for these generators. So how do we get current equation? So apply the KCL at this point. Okay, by KCL. Okay, by KCL, armature current IA is equal to the ISH plus IL value. Okay, this is the current in the current equations, right? So where ISH is equal to, how do we get ISH value? ISH is equal to the known parameter is the terminal voltage. So which is mentioned on the nameplate details. So that's why terminal voltage divided by RSH value. And IL, that is a load terminal, the load current. So output power divided by the terminal voltage. So after getting the current equation, now let us find out so voltage equations. Okay, how do we write voltage equation for these generators? Okay, so in the voltage equation, so by KVL equation, okay, by KVL, so apply the KVL in this loop. Okay, this value is equal to generated voltage is the voltage rises are equal to voltage drops. So that is a EZ is equal to, okay, EZ equal to VT plus IA RA plus, okay, plus the drop. Okay, here brush drop is a very small. So if brush drop is a neglected, okay, this value is a neglected. So therefore generated voltage is equal to the VT plus IARA, where IA is equal to the ISH plus IL. In separate exit generator, where IA is equal to IL. So next one, power equations. How do we get the power equations here? So that is the power equations. Okay, so power developed in the armature is equal to generated voltage multiplied by armature current. So these are voltage equation, current equation, and power equations for shunt generator. Similarly, another generator, so another self-excited generator, that is a series generator. So in series generator, the field winding is connected in series with the armature winding. Okay, where EZ is a generated voltage in the armature, VT is a load terminal voltage, IL is a load current, RAC the series field wind. So here always here shunt field winding has more number of the turns. So in this note here, very important, the shunt field winding winding as more turns with thin wire, got it? This is a shunt field. Shunt field winding as more turns with thin wire, and series field winding as less turns. The with thick wire. Okay, this is the design specification. So that, okay, here RSC value, okay, is a very small as compared to the RSH value. Okay, RSC is a very the small as compared to the RSC values. Okay, got it point. And similarly 5SC is a less as compared to, okay, 5SH values. Okay, this is a very important comparison point of view. The center field series field resistance is a less as compared to the RSH, and the series field flux is also less as compared to the shunt field flux. So now let us find out current equation initially. So in the generator, current equation. So in series generator, the field winding is connected in series with the armature winding as shown in the figure. How do we get current equation? IA is equal to ISC is equal to, so IA that is equal to ISC, so that is equal to load current, so that you can find out output power, the divided by terminal voltage, the VT. So this is the terminal voltage which is mentioned on the nameplate details. So now let us find out voltage equations, the first series generators. So apply the KVL in this loop. Okay, by KVL equation. Okay, by KVL. Okay, this apply the KVL in this loop. So generated voltage EZ plus, by KVL you can write VZ is equal to VT plus IA RA plus, okay, ISC RSC, the plus, okay, some amount of the brush drop. So if brush drop is neglected, then what will happen? So this EZ is equal to, okay, the VT plus, here IA IC, the both are equal, so that IA RA plus RSC values. So this is the voltage equation in case of the series generators. So next one, let us find out power equation. How do we get power equation in case of the series generator? So power equation is equal to, always power developed in the armature is equal to generated voltage the multiplied by armature current. So this is the voltage equation, power equation, and armature. So this point is a very important. The shunt field winding has more number of the turns. So because of this more number of the turns, pi sh is a more. The series field, the shunt field winding is designed with a thin conductor or thin wire, whereas the series field winding has designed with a thick conductor or thick wire. So shunt field winding has more turns with a thin wire. Series field winding has less turns with a thick wire. Okay. So next, another series generators is the compound generators. Okay, so compound generators are classified. There are the two classifications in the compound generators. So compound generators are classifications. One is a based on the connections of, okay, based on the connection, and also based on the directions of the flux. Okay, so first one we will discuss classification 1. Okay, so this classification 1 is a, so these are classified based on connection of shunt field winding and series field winding. Okay, such as, okay, one is a long shunt compound generators. Compound generator. So this is the based on the connections. Okay, long shunt compound generator. And second one is a short shunt compound generator. Okay, this is a first classification. So in long shunt compound generator, the armature winding, series field winding, okay, this one is there. Shunt field winding is connected across the combination of armature winding and the series field winding. Okay, suppose it is the armature winding. Okay, for example, armature winding terminal, and this is the series field winding terminal. So these two are connected in the series, right? So next one, okay, but the shunt field, this is the series, okay, series field winding, and shunt field winding, okay, terminals are connected across this part. Okay, this is the long shunt. So but in the short shunt, what will happen? Armature winding, okay, these two, the series field winding terminals are connected in the series. Okay, I will show the diagram later. So this is the shunt field winding is connected across the armature winding terminals only. So this type of two connection, the long shunt compound generator and short shunt compound generator. So this is the classification 1. Okay, compound generators are also classified based on the connections of the series field winding and shunt field windings. And next one, compound generators are also classified. So classification 2. Classification 2. Okay, so these compound generators are also classified the based on, okay, this is the based on the direction of series field flux and shunt field flux. Okay, such as, okay, such as one is a, okay, cumulative compound generators. Cumulative compound generators. Okay, and second one, so this is a cumulative compound generator and differential compound generators. Differential compound generators. Okay, got it? So in the cumulative compound generator, so net field flux is equal to phi net F, that is equal to, so phi SH plus phi SC. So both fluxes are adding, okay, in the cumulative compound generator. So next, differential compound generator, so phi net F is equal to net F, so that is a phi SH minus, so series field flux opposes the shunt field flux. In the cumulative compound generator, series field flux is aiding the shunt field flux, so that net flux is a more. So comparison point of view here, net field flux in the cumulative compound generator is a more as compared to the net field flux in the differential compound generator. So phi SH always is a greater than, phi SH is greater than the phi SH. Why? Because it is designed with a more number of the turns and it is designed with a more. So comparison point of view, net field flux, okay, net flux, field flux in the cumulative compound generator is greater than the net field flux in the differential compound generators. Okay, so due to this reason, okay, these two reason, compounding is possible in the cumulative compound generator. So due to which, okay, this is a, the due to which compounding is possible in cumulative compound generators only. So now we have a question. What is the meaning of compounding? Compounding is nothing but adjustment of the terminal voltage of the cumulative compound generator is known as a compounding. Okay, so we have a question here. So what is the meaning of compounding? What is meant by compounding? Okay, so this, what is the meaning of compounding here? Adjustment of the terminal voltage. Adjustment of the terminal voltage of cumulative compound generator is called compounding. Okay, compounding. Okay, so this can be achieved. How do we achieve this one? So this can be obtained by connecting the variable resistor. Okay, variable resistor. So no, it is treated as RD, diverter resistor, variable resistor across series field winding. Okay, got it? Fine. So that means here it is connected. Suppose here is there is some part of the field winding is connected in series with the armature winding. So it is the armature winding terminals. You can take long shunt and short shunt. There is no problem. So I have example point. I am taking long shunt generators. So some part of the field winding is connected in series and some part of the field winding is connected across the armature winding terminals. So this is the diagram for the long shunt component. So now load is connected here. So this is the load terminal voltage. Okay, this is the load here easy. Okay, sorry, load terminal load. So load terminal under no load condition. This is the generated voltage, the easy here. So this the switch is provided. So to operate loaded and the no load condition, and it is a load and it is the terminal voltage, the VT values. So in this case, here RSC value, okay, RSC and RSH. And how do we get compounding? Compounding can be achieved, okay, by connecting a diverter resistance. Okay, diverter resistance. Okay, this is the resistance value RD. So it is connected through the switch. Okay, here. So it is the RD value. So as RD increases, okay, this is the RD, the increases here. So we can, for example, the RD is equal to 0. Okay, then what will happen here? The total armature current passes to the diverter resistance. This is act as a, so when RD is equal to 0, so it acts as a shunt generators. Okay, got it? Fine. So when RD is equal to 0, so when RD is equal to 0, so what will happen? It act as, okay, act as a shunt generator here. So now when RD increases from the 0, okay, 0 to the some value, okay, from 0 to some value, so terminal voltage of the generator will be increased. Okay, increased from the shunt generator terminal voltage. So increased from the terminal voltage of the shunt generators. Okay, shunt generators here. So that's why it is called as adjustment of the terminal voltage. Okay, terminal voltage is known as a compounding. So based on the compounding, so these are classified as a three types. Okay, this one is, so based on the compounding, so based on the compounding or based on the adjustment of the terminal voltage, the differential compound generators are classified. Generators are classified into three types. So what are the three types? One is one is under compound generators. Okay, and second one is the plot compound generator. Plot compound or level compound generators. Okay, and third one is a over compound generators. Over compound generators here. This is the classification based on the compounding, based on the adjustment of terminal voltage. So these are classified as under compound generator, okay, plot compound generator, and the over compound generators. So now what is the meaning of exactly under compound, over compound here? So let assume, so this is the easy not, okay, easy zero, okay, this is called as a the no load terminal generated voltage of differential compound generator, no load condition. So this is the easy not in the means generated the voltage of the differential compound generator under no load, okay, under no load here. So it is a VT in the sense the load terminal voltage, okay, under node. So these are node terminal voltage. So under no load condition, VT is equal to easy not. Okay, got it point? So this under compound generator means the load terminal voltage, okay, VT, the less than the no load generated voltage. No load generated. And plot compound generator means the VT, the nearly equal to the no load generated voltage easy not. And over compound means, so this terminal voltage is greater than the easy not. Okay, we have to compare with the generated voltage, okay, terminal voltage under loaded condition and no load generated voltage. So in under compound generator, terminal voltage is less than the no load generated voltage. Plot compound generator terminal voltage is equal to no load generated voltage, and over compound generator terminal voltage is greater. So we are increasing the terminal voltage from what point here? So from the shunt generator terminal voltage to some other values. So that's why here we are adjusting the terminal voltage of the generator. So this adjustment is known as compounding of the generators. Okay. So now we have a question. How do we get the voltage equation, current equation, and power equation per long shunt compound generators? Okay, it is the VC and the VT. So first find out current equation. How do we get the current equations here? Just IA is equal to ISC, so that equal to ISH, okay, plus IL value. Okay, so this is the basic equation of armature current. So we know that how do we get ISH value? So where ISH is equal to RS, the VT divided by RSH value. So VT is given on the nameplate details. RS is also given on the nameplate details. So now let us find out IL. IL is equal to output power of the generator divided by the terminal voltage, the VT. Okay, output power divided by the terminal voltage. And let us find out this is a power equations. Okay, current the power equations. So first one, let us find out voltage equation. Okay, in the long shunt means here this shunt field winding is connected. Shunt field winding is connected. The series combination of across the series combination of armature winding and the series field winding. So that's why it is treated as a long shunt compound generators. And voltage equation point of view, apply the KVL in this loop. Okay, by KVL, the EZ is equal to the VT plus IA RA, okay, plus ISC RSC plus some amount of the brush drop. Okay, here IA and ISC both are equal, so that EZ is equal to the VT plus IA RA plus RSC plus brush drop. So if brush drop is neglected, so then the EZ is equal to the VT plus IA RA. This is the generated RA plus RSC values. Okay, it is similar to the series generated equation, but IA is the different, where here IA is equal to IL plus ISH. And how do we get power equations? Power is equal to power developed in the armature. So the equation is the same. So power developed in the armature is equal to generated voltage multiplied by armature current. Okay, power developed in the armature of the long shunt compound generator. Similarly, short shunt, another one. First one is the long shunt generator, and second classification is a short shunt generator. So in short shunt means shunt field winding connected across the generated voltage. Okay, but not the series combination of the armature winding and series combination winding. So now let us find out current equations for this. Okay, just here apply the KCL at this point. So IA is equal to, okay, here ISC is equal to IL, right? Okay, this ISC current passes the series field winding is equal to IL, where IA is equal to, okay, in this case ISH the place, okay, this ISH plus what will happen? Okay, this one is a ISH plus IL value. Okay, ISH plus IL. So where IL value is equal to ISH. Okay, now find out the how do we get IL? Okay, we know that IL is equal to output power divided by terminal voltage. Okay, next one, and ISH is equal to, okay, only this voltage, known parameter here. So that is the VT plus ISC RSC divided by, okay, RSH. So it is a very important. The how do we get the terminal voltage VT divided by ISH plus ET values? Okay, and next one, find out voltage equations. Second one, voltage equation. Okay, so this voltage equation is generated voltage by KVL, the VT plus IA RA, the plus ISC RSC, okay, plus some amount of the brush drop. So if brush drop is neglected, then remaining terms here, the EZ is equal to the VT plus IA RA, the plus ISC RSC. IA ISC both are not equal. So why? Because here ISC is equal to IL, IA is equal to ISH plus IL. So after getting the voltage equation, find out the power equation. So this power equation you can write. So power developed in the armature is equal to generated voltage and armature current. So like this you can calculate all the voltage equation, current equation, power equation for all type of the generators. Okay, so this concept is a very important. So it is a compounding in the, based on the compounding differential, based on the adjustment of terminal voltage. These are classified into the three types: under compound, plot compound, over compound generators. Okay. So this is the discussion of the today class. If you have any question, you can ask. So otherwise, I will wind it up. Uh, this is the official Creatrix channel which has 150K plus members in the Facebook. Please join in this group. And it is Unacademy GATE Telugu Telegram group. Okay. For any updates from the GATE Telugu group, please join in this channel. These are the different type of channels under the Unacademy. Creatrix GATE, the mechanical, Creatrix GATE EC, and Creatrix GATE Civil. Okay, Unacademy GATE Telugu, Electrical Junction, Unacademy GATE Questions, Unacademy Computer Science, Unacademy SSC JE, Unacademy Engineering Foundation, Engineering Patishala. Okay, thank you all. Thank you very much.